Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to discuss some of the properties of the definite integral. This first set of properties that we're going to be looking at are pretty trivial to prove because they're all simply based on the definition of the definite integral. Remember that we're looking at the limit as n goes to infinity of the Riemann sum. And then over here, I've simply put in what our delta x is, and then when we're looking at converting from the integral to the Riemann sum or back and forth, how we define that x sub I, right? And so when we look at these bottom couple of properties, then all you really need to do is convert from the integral to the Riemann sum, use what you know about the properties of limits and the sum, how we can distribute those, and then convert back over to the integral, and you'll see how these fall directly into place. Very simple proof. If you don't do it in your class, I urge you to do it on your own. You'll see how it falls nicely. For this property, we actually kind of almost proved this in the last video when we were simply doing the exercises. You saw how whenever we were dealing with this delta x, we just brought it outside of the limit here. And when we did that, you could see how easily that this was a constant term. Any of our constants would come out of the front, right? So any constant that we had in here would come out, and that works the exact same way for the limit here, okay? So one of the issues, though, that you might not have noticed initially, but we did discuss, would be this one. And the thing about this is that, again, if you simply run this through and run it through the Riemann sum, you see how that this is true, but you almost don't need to prove this one when you remember what we're talking about here. When we take this integral, we're talking about the area under the curve. But if we're looking at a curve that is simply a constant, then we're talking about a straight line at that value. So that means that we're looking at a rectangle because we have a flat line in the area under that line. And that's exactly what this is. This is just the area formula for a rectangle. It is a height times a width. So these two might not seem as obvious, but again, if you go back and you use what the definition of this delta x is, this one will make sense. Because if we're talking about the interval from a to a, that means that my b up here is also a. So a minus a would be 0, so 0 divided by n is 0, which means this is 0, so this whole term becomes 0. So that means that my integral is just 0. And again, here with this negative, it should make sense because b and a, when we're talking about the Riemann sum, we defined a as being the x0 and b as being the xn, right? So that meant that a was the smallest term and b was the biggest term. So if we flip those, that means that up here, we would be doing the smallest term minus the biggest term. Inherently, this would then become negative. So if this then becomes negative, that would make this negative, which would make this negative if we were to flip the interval around. So again, these are pretty easy to see and very easy to prove if you simply work your way through them using exactly the information that's given. The next set of properties we're going to look at are also pretty straightforward, but they're maybe a little less obvious. Now, the second set of properties are harder to prove at our level of calculus because they require a stronger understanding of set theory, specifically a stronger theoretical understanding of exactly what it means to be a closed interval. But you can understand them with a good geometric kind of demonstration. Now, the first one looks a little bit like one of the properties we looked at before, but I want you to notice that what we're talking about here is not adding two different functions. Instead, we're talking about the same function, but across an expanding interval. So in this situation, we have the same function, but here we had it on one interval, and then we stretched it across more of that interval. And specifically, that interval was continuous from one point to the end of the next point. There was no break here. We went A to C and then C to B, which is why we kind of drew it graphically to show what we're talking about. We said that we started here and then we went to here, so we could rewrite it as this interval. Okay, so we could rewrite the two intervals, the two integrals with different intervals, as one integral with a single interval from A to B. Okay, that's a little bit different than the property we showed before. And it should make sense because remember that we're talking about this function having to be continuous on this closed interval and on this closed interval, but this closed interval meets up here. So it should work out fine. And it does work out specifically because we're talking about the Riemann sum. So it doesn't actually matter that maybe here the sums were different size than the sums here, because when we put it back together here, we'll repartition out the interval, but it didn't matter because both of these intervals were fully partitioned. Okay? But again, that's not a robust proof. Now, when we talk about the next one, this and this proof both should absolutely make sense, because what we're saying is that if f of x is greater than 0, then when we talk about the area under the curve, the area should also be greater than 0. And again, that should make sense because if the area is above the x-axis, how would we get a negative value? There's no negatives, right? And then here, if f of x is greater than g of x, that means that the area of f of x should contain the area of g of x. Again, because if f of x is here and g of x is here, and we're talking about the area under f of x, well, if g of x is below f of x, g of x is contained in the area of f of x. Again, that makes sense. Which is similar to what's going on here, but the reason I wanted to draw out this bottom one is because it's a little bit weirder, because we're talking about having a constant being less than our function, which is less than another constant. And then here we're not talking about the interval, except that we are, because if you remember our previous property, this is actually just the integral of this, and this is the integral of this. So really all we've done here is we've taken the integral of each of these. So this last property is simply applying this property, but with constant values. And if we draw it out, it should again make sense, because we said that this constant is less than this function on this entire interval. So that means that our constant is below our function everywhere. So again, the area below our function contains this rectangular area. But then our function is in turn contained by this rectangular area. So effectively, these two constants kind of set up boundaries for containing this function. And there are places where this is useful for basically kind of setting up bounds where we know kind of a space that our function will be contained within. You can think of this almost like kind of the integral version of like the squeeze theorem a little bit. Not quite, because it's not the same thing, but it's kind of similar. Okay? So basically, you've seen some properties, so next, go ahead and apply them. So I hope you found this overview of some of the properties of the definite integral helpful. If you have any questions, you can always drop into the comments below or join us on Discord. And as usual, the answers to the exercises will be after this outro.